Society. Professor Vujic.
Good morning, everybody. And just a moment, I would like to share the screen. I hope all of you could see the slides. If you don't, please send a chat to Charlotte and she will be able to help you out. First, I would like to thank everybody for joining us this morning. And as Bethany mentioned, we have more than 60 people joining us. Also, I would like to thank all of our students who actually volunteered to give their presentation, because UPR meeting that was supposed to be at this time has been canceled due to COVID-19. These 16 students that volunteered to give presentation actually are graduating within a year, and they're looking for the position in national laboratories. And today we will have a large number of our colleagues from national laboratories and the government that will be listening to student presentation. Let me give you an overview of what NSSC is and what are some matrices of success. And tomorrow I will present the highlights of research. So our objective from early on was first to recruit and train top students in relevant nuclear disciplines, then to connect our students with core set of disciplines that I will show in a minute, and in support of the non-proliferation and nuclear security mission, and then to expand our collaboration with national laboratories so that we can provide to our students opportunity to engage deeply in research under the guidelines of lab scientists. Currently, which is our NSSC 2, we have 7 partnering universities that are shown on this map, and 5 national laboratories that collaborate with us. This is our organizational chart. As you can see, we have executive team. I am the director and principal investigator. Bethany, that you just met a minute ago, is our executive director. Deputy executive director is Jason Hayward from UTK, and NSA liaison is Kai Vetter. And director for the laboratories is Lee Bernstein. This executive team meets every week. Then we have our point of contact council that consists of university point of contacts colleagues, laboratory point of contact colleagues, and then on top of it, we have advisory board that I forgot to mention. Point of contact council meets every month to direct our research and to discuss about what we accomplished that particular month. And then we have advisory board, which meets once a year to review our accomplishments and to give us guidelines for the future work. We are proud to have great people in our point of contact council as well as in our advisory board. And not to forget, we have our NSSC support staff. Program manager is Charlotte Carr, and financial analyst Derek Johnson. So we are very lean on the management and administration. Next slide shows 4 of our research focus areas and 4 cross-cutting areas. So as you can see, we accomplished a lot within this particular set of disciplines that we are covering and doing research. I will be talking about the highlights tomorrow, but today I will just mention the areas. So we have nuclear and particle physics, which is led by Barbara Jacek, and co-lead is Sean Liddick from MSU. Radiochemistry and forensics, Ken Chervinsky and John Arnold from UC Berkeley. Nuclear engineering, led by Max Vertoni and Philip Burdett from GW. Radiation detection, led by Kai Vetter and Jason Hayward from UTK. And then we have For cross-cutting area, nuclear data led by Lee Bernstein, modeling and simulation by me, nuclear security policy by Michael Nacht, and education and training by Bethany Goldblum. Today, for our first day of showcase, we will have students presenting in the area of nuclear and particle physics, as well as in nuclear security policy cross-cutting area. Short history, because this is our NSSC 2. So NSSC 1 was established in 2011 as the first NNSA funded academic consortium. So we are very proud, and you can see on the picture top left, Ed Watkins, Dave McGrath that came for our kickoff meeting in June 2011. We didn't get funding because of long negotiation between UC Berkeley and DOE before January of 2012. So we practically started working in 2012. At that time, we have 5 focus areas, which are listed, very similar to what we have now. And we also established the first new course, which was on nexus between nuclear security policy and technology. And this course has been offered since that time. We also started with our monthly webinar series, in which we invited our colleagues from National Laboratory to present their work and their research. Then we started with a large number of summer programs, including Los Alamos summer program that was much shorter than what we have right now. And also in 2014, we supported 5 minority serving institutions through research grants that we awarded to them and through internship. At the end of NSSC 1, we had 127 undergrads that we supported, 139 graduate students, 34 postdocs, and 42 faculty members. In NSSC 2, which we are now in the 4th year, starting with the 5th year, we competed, we won again, we are very proud of it. And this time around, we are trying to do it the 3rd time. So we expanded our partner list to UTK, Texas A&M, George Washington University, and we added Oak Ridge National Laboratory. In September of 2017, we started with our annual workshops and also advisory board meetings that we held since then in each of our neighboring national laboratories, first at Lawrence Berkeley, then Sandia, and then Lawrence Livermore National Laboratory. In 2018, we started with the Nuclear Security Policy Bootcamp that was held at Washington, DC, and organized by George Washington University. So we are proud that at the end of these 9 years, we can say that 112 NSSC alumni are now working in national laboratory and the government. So overall, this is a kind of summary. So we were able to support either fully or partially 521 people, including 168 undergrads, 227 graduate students, 47 postdocs, 63 faculty, and 16 specialists. Out of that, 31 are female students, so we are very happy about it. And so far, 108 PhD degrees were completed, 67 master degrees, and 112 Bachelor of Science degrees. We are proud to have a line of PhDs, masters, and bachelor that will be graduating during the next year. So how did we accomplish all of that? What is our matrix? So first, this is the quality of our students that we recruit, and also the quality of research that they're engaged in, thanks to our faculty and thanks to our national laboratory mentors. So each of our students does have a mentor in one of collaborating national laboratories. So as you can see, our students and faculty published 333 peer-reviewed publications, were awarded 176 awards, And then we have over 500 poster presentation and close to 800 oral presentations. So just to emphasize the awards, we have Dane Danielson from UCD and Travis Smith from UTK, who won 2019 Innovation in Nuclear Technology R&D Awards. And then we have Kevin Glennon for Texas A&M that won Outstanding Presentation in Chemistry at Los Alamos. In addition to regular courses and research that our students are required to do, we have very rich summer programs for our students. And over the last 9 years, NSSC has supported 39 summer schools and summer programs, including some of those that are listed here, such as UC Davis Nuclear Analytical Techniques Summer School, then George Washington Boot Camp for Nuclear Security Policy. And we started with NSSC program in NSSC1 and then expanded it to 8-week summer program that we organized in collaboration with Los Alamos colleagues 3 times, 2017, 18, and 19, with over 60 students that participated in this program. So what was our goal with NSSC Lano Keeping Non-Proliferation Summer Program? First, to create working relationship between NSSC student and our Los Alamos colleagues. Then to increase number of students performing programmatic research at Los Alamos, and also to turn research and training to careers in national laboratories. So just to mention few of students that are listed here, received after attending this summer program, they received a Seaborg Summer Fellowship to return to Los Alamos. Program is 8 weeks, 2 weeks, first 2 weeks are dedicated to touring the lab, listening to highlights of research of different colleagues from Los Alamos. And then for 6 weeks, our students actually engage in research, working in particular research groups that we were able to match student interest and research group interest. This time, we're also trying to do it virtually because unfortunately, the program has been canceled. However, we are now offering a non-proliferation science summer program that will be virtual. Students will be fully supported and with laboratory mentors. So you see some of the pairs on the right. And also the first 2 days of keeping program lectures will be available to all participants, including members from other NA22 consortia. In addition to this virtual summer program, we are also working on the development of another learning experience for our students, and this one will have virtual experiments. So this is with Lawrence Livermore National Laboratory, and I would like to thank our colleagues from Livermore, particularly our POC, Vladimir Mozin, which is working very hard to make this happen. So objectives of this virtual program is support of the education program, provide data from laboratory for all these experimental demonstration, and benefit also research project for our students. So what will be available? We will have neutron generators, we will have gamma ray sources, we will have gamma ray detectors, neutron detectors, imaging systems. Then we will have all kind of low Z and high Z shielding materials, plutonium material samples, uranium mass and enrichment standards, and all kind of containers and enclosures for our students to work on. So this is exciting programs, and we are very happy to participate in that. In addition to summer programs that our students are mostly required to attend, some are voluntary. We developed specifically for NSSC students additional courses, and this is a list of 9 courses, and we have several that are not listed here that are held at UC Berkeley, UC Irvine, UC Davis, and UTK. From the policy, which is nuclear security, the nexus between policy and technology, that is co-taught by Michael Nacht from School of Public Policy, as well as our nuclear engineering faculty. Carven Bieber has been co-teaching this for last several years. And the idea behind is to put together nuclear engineering students and policy scholars and history majors you know, in one room, as well as natural sciences students, to discuss different topics related to nuclear security policy and technology. The next also developed at UC Berkeley. So the first one was established in 2012, and the next one was established actually last week in order to recruit new students at freshman level. So this is a hands-on introduction to radiation detection, and Ellie Hanks was developed and taught this course. So she basically offers students introduction in everything related to what radiation is, how we detect it, how we can find it, see it, and also students learn about detection, about instrumentation, and at the end they create their own small Geiger-Miller counter that they can take home. So this was really exciting. The other courses, nuclear data, UT Knoxville, radiochemistry method in nuclear technology at UC Berkeley, radiation detection and nuclear instrumentation, also UC Berkeley. And just to mention several added nuclear focuses on UC Irvine, nuclear in radiochemistry also at Irvine, and designed emphasis in nuclear science at UC Davis. In addition to summer programs and courses, we develop a series of webinars that we held since 2013-14. It's mostly monthly. Sometimes we have more than one webinar. We are broadcasting them. In 2019-2012, we selected some of these that you see listed. And we are very happy that our colleagues from national laboratories are participating, and they're very happy either to come or to give virtual seminars. I would like to particularly emphasize very interesting panel that was held in Berkeley in collaboration with NSSC. When we had a panel discussion on interesting topic, how close are we to doomsday, nuclear dangers, and stopping a new nuclear arms race, with panelists such as former US Secretary of Energy, Dr. Ernie Moniz, former California Governor Jerry Brown, and our own Executive Director, Bethany Goldblum. This was very well attended and excellent panel. And to summarize what we accomplished so far, we see that almost linearly we increase in number of awarded degrees. So currently we have 108 PhD degrees, 67 master, and 111 bachelor degrees awarded to students supported by NSSC. In terms of where do our students go, because we are supposed to be a pipeline of great new scientists and researchers going to national laboratories, we are proud to emphasize that 112 at this moment, and we have several lined up, are employed by one of 5 national laboratories that are collaborating with us and other government, which is 42% of those that we supported that graduated. The other government positions are at DOD, DOE, NNSA, JITRA, Air Force, US Navy, and so on. 50 went to academia to teach the next generation of scientists and researchers in these areas, and 55 in field or industry. regarding what laboratories they went to, you have here a table with list of 5 collaborating laboratories, and then other labs and the government. And vertically on the left, you have our collaborating university partners. So we see that 112 in some laboratories, we have more people, such as Livermore 27, which is understandable because they're close by, but also other lab and government, we placed 40 of our students. With that, I would like to thank you for attending again our seminar, and I'm open for questions.
Thank you very much. So does anyone have any questions? Okay, at this point, we're gonna have, we're having some technical difficulties. So at this point, we're gonna have Charlotte go ahead and queue up Andrea's slides. Andrea, are you ready?
Yes, I'm ready.
Okay, great. It's my great pleasure to introduce Andrea Richard. She is a postdoctoral scholar at Michigan State University, and she's going to be talking about indirect neutron capture constraints for basic research and applications.
Okay. Here we go. Sorry. Okay. So good morning, everyone, or good afternoon, depending upon which time zone you're in. Thank you to the NSSC for giving me the opportunity to present at the Virtual Scholar Showcase, and also for just giving us the opportunity to engage with the national laboratories like this. And thank you to all of you for listening. So the title of my work that I've been doing over the past few years is Indirect Neutron Capture Constraints for Basic Research and Applications. My name is Andrea Richard, and I'm currently an NSSC postdoctoral fellow at Michigan State University. I work at the National Superconducting Cyclotron Laboratory, which is a radioactive beam facility, and I work with Dr. Sean Liddick. My NSSC laboratory mentor is Dr. Aaron Couture at Los Alamos National Laboratory, and he works in the P27 division. And the main focus of my work, as well as the work that we've done a lot at Michigan State University, is indirect neutron capture constraints on short-lived nuclei, both for basic research as well as applications. And this has a direct relation to the NSSC focus area in nuclear and particle physics, and it crosscuts as well with radiation detection and instrumentation and nuclear data. And neutron capture cross-sections are important for a wide variety of purposes, both on the basic nuclear science side, as well as for applied things in the NNSA mission area. And so, for example, I'm showing this reaction network over here, which is important for yield diagnostics, and you'll hear more about that later in some of the later talks. But what we really want to try to understand is the competition between neutron capture versus beta decay versus other neutron-induced reactions that could occur in these sorts of networks. And these reaction networks play key roles in nuclear energy and also for basic nuclear science and our understanding of the probability for when reactions occur or how strong they might be, as well as for astrophysics and our understanding of the synthesis of heavy elements above iron. And this informs future discoveries as well. But if we, and so you'll see more about this actually in presentations both by Adriana Sweet and Katherine Childers in this same session, so stick around and you'll hear more about all of these sorts of things. If we look globally, however, at the number of neutron capture cross-sections or rates that have been measured, if we look across the entire nuclear landscape, which is a visual representation of all of the known nuclei, both stable and unstable, what you can see is that the majority of the neutron capture rates or cross-sections that have been measured all lie very close to stability, and very few have been measured for short-lived or radioactive nuclei. And so the radioactive nuclei are the ones that play key roles in both the NNSA mission areas as well as for astrophysics and basic science. And so that really drives us to go out and start trying to measure some of these radioactive nuclei and specifically their neutron captures. So how would we actually do that? Ideally, we'd want to do some sort of direct measurement where we have our neutron coming in and impinging on our A-1 target to create this A star nucleus that's of interest for some application. However, for short-lived nuclei, the targets that we would make are prone to decay. They have short half-lives. The neutron itself is also prone to decay, and so at this point in time, there's no feasible neutron target. So this sort of direct technique is just not really possible at this point in time for radioactive isotopes. And so instead, we turn to indirect techniques that will allow us to access the same nucleus through a different pathway. And so we still want information about this A star nucleus, but we're using X as a means to populate that. And in this way, we can actually utilize the fact that these nuclei have short half-lives. There's a whole host of different examples of indirect techniques that you can use, and I've listed them, some of them here, but the technique that I'll be talking about today is the Bethe-Oslo method, which was a method that was developed a couple of years ago in collaboration between Michigan State University and the University of Oslo in Norway. So the Bethe-Oslo method relies on the statistical neutron capture. And so in statistical neutron capture, we utilize something called Hauser-Feshbach theory to describe the cross-section. And the cross-section in Hauser-Feshbach theory can be approximated as taking into account three main ingredients. First, the nuclear level density, which is the number of levels per MeV. Second, the gamma ray strength function, which describes the probability for a gamma ray to decay from a particular level in the nucleus. And lastly, the optical model potential that describes the interaction between the neutron and the nucleus that it captures on. And so if we run one of these neutron capture cross-section calculations in a statistical reaction code such as TALIS, and the example that I'll show today is strontium-95 in gamma, which you might remember played a role in that reaction network that I showed. If we first run this calculation to determine the cross-section, and we vary all of the available level density models, some of which are listed here, you can see the uncertainty that that induces in the cross-section. If we then do the same thing for the gamma ray strength functions that are available as the models in TALIS, you see an even larger band of uncertainty. And then lastly, our third ingredient, the optical model, in this case doesn't play as much of a role in the uncertainties because of the fact that this nucleus is a little bit closer to stability, but we do anticipate that this would get worse as we go farther from stability. And so if we combine these three pieces of information and then try to constrain our cross-section, we end up getting a cross-section that's about an order of magnitude uncertain. And so what that means is that our ability to do anything predictive in reaction network calculations or for astrophysics is severely limited because the uncertainty is just so large. And so we actually want to go out and start trying to measure some of these to constrain these cross-sections and reduce the associated uncertainties. And so the way that we do that at Michigan State University is we use beta decay total absorption spectroscopy to infer the neutron capture cross-sections. What we do is we use beta decay as the mechanism to populate states in the nucleus that we're interested in measuring, and then we extract the level densities and strength functions from that. What we need for this technique is the total excitation energy of the daughter isotope. We can't use the beta decay electron in this case because of the fact that beta decay is a free body decay process. So instead we measure the total emitted photon energy. So in this schematic example, what we want to have access to is both the individual gamma rays as well as the sum of those two gamma rays giving us access to the total excitation energy. But this technique requires us to have a very high detection efficiency to be able to access the total excitation energy. But once we have this, we're then able to extract the level density and strength function, insert both of them into a statistical reaction model to constrain the neutron capture rate. The detector that we use at Michigan State University is the SUN detector, or the summing sodium iodide detector. It's a large size, high efficiency total absorption spectrometer, where summing across the entire detector volume gives us access to information about the excitation energy, whereas segmentation, a single segment corresponding to 3 of these PMTs, gives us information about individual gamma rays. As a practical example, we can take cobalt-60. Cobalt-60 beta decays to 2 different states in nickel-60. So within a particular segment of sun, we expect to see these 2 gamma rays. And so this is what a segment of sun would look like. But in the total absorption spectrum, or the summing spectrum, you would expect to see these 2 gamma rays summed, and you get a peak around 2.5 MeV, which corresponds to the sum of these 2. And so because of the fact that we now have access to both the individual gamma rays as well as the total excitation energy, we're then able to do the Bethe-Oslo method. So the Bethe-Oslo method is used for inferring neutron capture rates. What we obtain experimentally is a raw matrix that looks like this, where we have excitation energy along the y-axis and then gamma ray energy along the x-axis. And this is our experimental Oslo matrix. That's what we refer to it as. And so what we do is we unfold this matrix to remove the detector response, and then we need to extract primary gamma rays from the cascade from this experimental spectrum. A primary gamma ray is the first gamma ray that's emitted from each level in the nucleus. And then we extract these primary gamma rays and we use those to get our level density and our strength function. We then have to normalize our data to 3 normalization points. First is the low energy level density. And so this comes directly from nuclear data. And so we just look in the NNDC, see what's been measured before, and we use that to constrain our level density and strength function. Second, we need the level density at the neutron separation energy, which for radioactive nuclei, we use models to constrain that. And then lastly, for normalization, we use the average radiative width at the neutron separation energy. The 2 cases that I've looked at during my time as a postdoc at MSU is the beta decay of niobium-103 to molybdenum-103 and niobium-104 isomeric state to molybdenum-104. These isotopes are important both because of the fact that they're fission fragments and also because they play a role in astrophysics. So the experimental spectra that we've obtained from this work, shown here again with excitation energy on the y-axis and then gamma ray energy on the x-axis. After going through the steps in the Oslo method to first remove the detector response and then isolate the first gamma ray emitted in each cascade, I end up with a primary gamma ray matrix that's shown here. And then I extract my level density and strength function within this region that's outlined here. So the nuclear level densities for molybdenum-103 and 104 are shown here. Just as a reminder, the level density is the number of levels per MeV. And so at the very low excitation energies, you can usually count these by hand because these are discrete levels where you'll have maybe 1 or 2 levels. But as you go higher and higher in excitation energy, you start to reach the continuum. And at that point, you can no longer count individual levels. And so this is the statistical region that we're looking at. The data points in this case come directly from that primary gamma ray matrix. And we then have to normalize, like I said, at the low energy to the known levels. That's what's represented here. This comes directly from nuclear data. And then at the high energies, we normalize using theoretical models to figure out what the level density should be at the neutron separation energy. After we have our level density, the second ingredient that we need to be able to constrain the cross-section is the gamma ray strength function. For this, however, we do have to take a step back and consider the fact that we are using beta decay as the mechanism to populate this nucleus that we're interested in. And beta decay is a very selective process. And so for allowed beta decay, you see a change in spin of only 0 or 1. And then after that, we assume a dipole transition. And so what that would mean for a 4- state is that you could expect to populate spins between 2 to 6. So that means that we only populate about 51% of the total level density outlined in this box that's here. And so we have to reduce our level density by that amount before we're actually able to extract our strength functions. The strength functions that I extract after correcting for the spin population are shown here. These represent a probability for a gamma ray to decay, and it's our second ingredient that we need in order to actually constrain a cross-section. So after we have our two experimentally constrained cross-sections, we can put both of those things into a statistical reaction code. In this case, I've used TALIS. If I run TALIS out of the box with all of the different default level densities and strength functions, I end up with a band of uncertainty associated with molybdenum-102 in gamma and molybdenum-103 in gamma. That's represented by this purple-gray color. And so you can see that it's about an order of magnitude uncertain. However, once I put in my experimentally constrained level densities and strength functions, we're able to reduce this uncertainty to this blue band that's shown here. And so this is a significant improvement. And these cross-sections are currently being put into reaction network calculations to determine their impact. Today, I've told you that neutron-capture cross-sections are important for a wide variety of applications, both on the basic science side as well as for applications. I also told you about the indirect techniques and how they're required to constrain neutron-capture cross-sections for short-lived nuclei, and that at MSU, we've developed a program to do this using the Bethe-Oslo method. The neutron-capture cross-sections for molybdenum-102 and 103 in gamma are complete, and the impact of those newly constrained cross-sections is currently underway. And something that we're really excited about and looking forward to in the future is the upcoming facility for rare isotope beams, which will be built on which is currently under construction and to be completed soon on the campus of Michigan State University. And we will be able to use the Bethe-Oslo method on a variety of isotopes that are much farther from stability than we've ever been able to do before. And so we're really looking forward to continually applying this program to more and more neutron-rich nuclei. This work could not have happened without all of the amazing collaborators that we have for Bethe-Oslo, both from the national laboratories and universities, both domestically and abroad. And so lastly, I just want to talk about my NSSC experience. I did my graduate work at Ohio University. I got my master's degree in 2014 in neutron time of flight spectroscopy, and then my PhD in 2018 doing beta decay and gamma ray spectroscopy for nuclear structure purposes. I then started as an NSSC postdoctoral fellow at Michigan State University in 2018. And while working with the NSSC, I've had the opportunity to present my work at several of the fall advisory board meetings, as well as the 2019 University Program Review. And as a direct result of the University Program Review, we've developed a collaboration with the University of Michigan and the Consortium for Verification Technology there, to actually use some of their novel neutron detectors for work that we could do at Michigan State University. And so that's something that I'm really looking forward to. And I'm also currently collaborating with my laboratory mentor, Aaron Couture, for a future proposal submission at Lance using the dance detector. So the last thing that I'll just mention is that also in collaboration with the national laboratories, specifically Livermore, Argonne, and Berkeley, we just completed a campaign of experiments at the NSCL using the germanium clover detectors, which are pictured here. And additionally, we currently have a campaign of experiments going on at Argonne National Laboratory using the sun detector as well as the tape station. And you can see us here installing some detectors for this. And I spent a lot of time working on this over the past couple of months and trying to get everything ready for the campaign that we have using the Caribou fission source there. And so I'm in the last year of my postdoctoral research at Michigan State University, and I'm looking forward to future opportunities at the national laboratories. So with that, I would like to say thank you to the NSSC for allowing me to speak here and also for their generous funding and support. And lastly, thank you to all of you for listening.
Yay. It's hard to clap with only one mic, but I'm sure we're all 60 plus of us are at home cheering. Great job, Andrea.
Thank you.
So we do have a question from the audience. So will the method work for all short-lived radionuclides, and why or why not?
That's a good question. So there are some criteria that you do have to meet to be able to use the beta-Oslo method. So first, the nucleus should beta decay. So I guess that's the first thing. But also the beta decay Q value has to be high enough that we would actually be able to expect to populate states in the statistical region. So if the Q value is too low or the neutron separation energy is also low, then we won't really be able to apply this technique because it is a statistical technique. And so there would be some cases where it might not necessarily work. And in those cases, we would turn to other techniques like the surrogate method or something like that.
Do we have any additional questions? So it is my understanding that Andrea will be completing her postdoc within the year or two, so at least perhaps within a few months. So I don't know.
Just one question. Could you hear me?
Yes.
I know that your work was mostly experimental as well as theoretical. Could you tell me how this COVID-19 closure affected your work, and are you going back to the laboratories?
Yeah, sure, I can talk about that. So for the beta decay campaign that I mentioned, we actually finished all of our experiments before really like the lab closed down or anything. And so it didn't really impact like those measurements. And right now I'm working on analysis. And so I am able to work from home, but the user program at the NSCL has sort of been put on hold and we're just now starting to get back into it. But the one thing that was majorly impacted was the campaign of experiments at Argonne National Laboratory. They've sort of been delayed a little bit. And so we're a little bit playing it by ear to see how that campaign of experiments will end up going and what that timeline will look like. But for the most part, I'm spending a lot of time at home in my apartment doing a lot of analysis.
Okay, great. Thank you very much. This was excellent presentation.
Thank you.
Okay, thank you guys. So now it's time for a break. So we're going to be back at 9:35 and we'll start promptly at that time. I see Kaylee with a hand. Kaylee, I don't know if you can hear me, but if you can, and you do have a hand raised, you can send a note in the Q&A. We've disabled the chat. No problem. There's all sorts of tricky features, so just wanted to make sure that you had everything that you need. And while we're waiting, another thing that I wanted to mention is that if you navigate to the event website, you'll also find a link there to our most recent newsletter. This was distributed with your invitation, which should have included a private link to this webinar. But you can download the newsletter there and read about our students and their accomplishments and some of the events that we've held over the past year. So I encourage you to do that in the meantime, and we'll be back at 9:35. Hi, folks. If you're joining us late this morning, you can find a link to our event webpage in the chat. It should also be in the registration email that you received. And from there, you'll be able to download our most recent newsletter, which has lots of interesting highlights from student accomplishments over the past year. So we're going to get started again in about 2 minutes. Good morning. Welcome back to the NSSC Virtual Scholar Showcase. This morning's session, as you can see, is mostly nuclear and particle physics, and we have one nuclear policy talk. It was organized in this way so that we could organize our lab colleagues to be able to attend those sessions that were of the most interest for their programs. And so what you're going to hear now is a talk from Adriana Sweet, who is a graduate student, soon to be Dr. Sweet at UC Berkeley. And she is also going to be discussing the use of the Bethe-Oslo method for indirect neutron-capture cross-section measurements, in this case for applications in stockpile stewardship and nuclear forensics. So, Adriana.
Thank you. Thank you for that wonderful introduction, Bethany. I'd like to introduce myself a little further. My name is Adriana Sweet, and I'm a graduate student at UC Berkeley. And today I'll be presenting to you the results of my thesis work. So I'm a graduate student at the Department of Nuclear Engineering at UC Berkeley. And this summer I'll be filing the results of my thesis work. My academic advisor is Professor Jasmina Vujic, and through my years at Cal, my lab mentor who's supported me has been Dr. Darren Blohl at Lawrence Livermore National Lab. My work has been really the result of a fruitful collaboration between Lawrence Livermore National Lab and the National Superconducting Cyclotron Laboratory. My work has a range of impact, from curiosity to application-driven programs, some of which I have listed here. In specific, I'll focus on the motivation behind my work, which is the science-based stockpile stewardship mission. I'll begin with a little bit more in-depth view of the reaction network pictured here. This reaction network represents a number of events that occurs during and after a fission event to fission fragments of the A=95 mass region in a high neutron field. To the right of the figure, you see a importance factor, which describes the nucleus of importance in terms of a independent mass yield and a mass-dependent term. The importance factor really describes where we should focus our analysis to improve the nuclear data. For instance, importance factors of bright green indicate the most importance. In this case, for instance, strontium 95 is given a high importance factor. The importance factor dictates the priority we should place on improving our nuclear data. And in this case, strontium 95 is important as it goes on to beta decay to zirconium 95, which is measured in debris following the yield to determine the yield of a nuclear device. Because we're interested in the formation of strontium 95, we therefore are also interested in the properties of its parent nucleus. Thus, improving knowledge of lighter strontium isotopes, such as strontium 93, is also important. It's only 2 neutron captures away from strontium 95. And understanding its statistical properties can help us improve knowledge of the production and destruction rates of strontium 95. At Michigan State University, we conducted an experiment using a radioactive isotope beam to produce strontium 93. This work resulted in a suite of techniques and methods to determine the cross-section. This will prepare us for the day we can also utilize a high-intensity beam at Argonne National Lab to study strontium 95. As an overview of the experiment, here I present a few key points, beginning with the radioactive isotope beam utilized, which was the decay parent, rubidium 93. Rubidium 93 decays to strontium 93 within 6 seconds. Strontium 93 also beta decays to yttrium 93. Yttrium 93, the decay daughter, acts as a contaminant to our measurements, and I'll explain this in further detail in the following slides. Other key points of this experiment includes the kinematics of the decay itself. The Q value is significantly higher than the neutron separation energy, which allows access to highly excited states. In addition, the total absorption spectroscopy technique allows us to measure simultaneously individual gamma rays as well as the excitation energy. In combination, the Bethe-Oslo method utilizes this detection technique and the kinematics itself to extract nuclear properties. Andrea Richards, who you've just heard from, presented you with an overview of this method in great detail. And here I'll just reiterate some of the key points in that the Bethe-Oslo method extracts statistical properties, the nuclear level density and gamma ray strength function, from highly excited states in the compound nucleus, in this case, strontium 93, which was formed through the beta decay of rubidium 93 to strontium 93. The measured gamma rays, which I'll discuss next, are the measurements utilized to get those properties and then eventually use them in reaction codes such as TALIS to calculate the neutron-capture cross-section. The experimental setup includes the summing sodium iodide detector, which you've received a presentation on by Andrea Richards as well. I'll discuss SUN in combination with a plastic barrel scintillator detector as it pertains to my experiment. Pictured here is SUN labeled as 1 and the barrel detector labeled as 2, which was placed at the center of SUN in the borehole, so as when a beam of rubidium 93 is delivered to our experimental station, it implants at the center of SUN upon a 9-track tape. This beam implants the rubidium nuclei, which beta decay, emitting beta particle and gamma rays simultaneously. Our detector setup enables us to obtain coincidence measurements. After 60 seconds of implantation, a motor-actuated tape box rotates this tape out of our detector setup so as to minimize contamination from the decay daughter, which I will discuss next. But as you see here, this system allows us to limit contamination and maintain high statistics. The measurements obtained using this detector setup includes both the excitation energy and the gamma ray energy. Pictured on the left, you see the activity as a function of time for theoretical decay and production curves of rubidium 93 and strontium 93. you can see that within a few seconds, rubidium-93 saturates. This is advantageous such that the contamination level is maintained at a relatively low level. In this case, for 60 seconds, the contamination level is only about 4%. Plotted on the right is a graph of counts per 20 kV as a function of excitation energy. In addition to a low contamination level, you can see here in the comparison between the raw total absorption spectra and the daughter subtracted total absorption spectra that the decay daughter really only affects the low excitation energy region. Thus, by placing a threshold on the excitation energy of 4 MeV, we can decrease the impact of the decay daughter on the analysis of our measurement. In addition to the excitation energy measured, the gamma ray energy was measured, thus creating a 2D histogram of excitation energy as a function of gamma ray energy. This is the probability matrix that Andrea described. This is what is analyzed using the Beta-Oslo method. Here is a graph of the counts per 20 kV as a function of gamma ray energy. Once again, the plot illustrates the comparison between the raw data and the gamma ray spectra with the contamination removed. I've also included the decay daughter gamma rays measured. And you can see here that the gamma ray energies, just like the excitation energies, were relatively low in energy. Thus, by placing a threshold at about 1.5 MeV, we can limit the impact of the contamination in the analysis. So the first two steps included the detector response and extracting the primary gamma rays, which Andrea spent some time on. Here I'll focus mainly on the extraction and normalization of the statistical properties, beginning with the nuclear level density. Here is a plot of level density as a function of excitation energy. The gray histogram represents known levels for strontium-93. The violet histogram represents known levels obtained through beta decay experiments. In addition, here I've plotted estimates at the neutron separation energy of the nuclear level density. I'll explain these estimates in the following slides. The nuclear level density obtained using the Beta-Oslo method has a multitude of solutions. These solutions are equivalently good. However, they are not necessarily the physical solution. To determine a physical solution, external data is used to normalize the nuclear level density. There are two normalization points in obtaining the most physical nuclear level density, the first being discrete levels at low excitation energy, and the nuclear level density at the neutron separation at high excitation energies. This estimate was obtained through different normalization approaches, such as investigating microscopic models, such as the Hartree-Fock-Bogoliubov model, as well as estimates based on neighboring stable nuclei and the available neutron resonance data there. Here's a plot of the nuclear level density as a function of excitation energy, where I've plotted my experimental data labeled as norm 1 and norm 2. These normalizations represent a upper bound and lower bound normalization approach to the nuclear level density. In addition, I've included the Thales default calculation using the Hartree-Fock-Bogoliubov tabulated level density to illustrate the relative terms of where my experimental data lies to theoretical models. Once obtaining a normalization for the nuclear level density, I then normalize the gamma ray strength function, which depends on the nuclear level density to determine its shape. These are interdependent nuclear properties. The final normalization point is the radiative width, as well as the average neutron resonance spacing. For stable nuclei, these pieces of nuclear data are known. However, for unstable nuclei, such as is the case for strontium-93, this is unknown, and an estimate was obtained using known widths of stable neighboring nuclei. Here is a plot of the gamma ray strength function for dipole transitions as a function of gamma ray energy. The curves in green and various line styles represent represents theoretical models for the gamma ray strength function. The magenta data points represent the photoabsorption data available for strontium-88. This is the last strontium nucleus that we have data for up till this point. Included in this plot is experimental data of my own analysis, which includes the normalization 1 and 2, which represent a upper bound and lower bound constraint on the gamma strength function. These nuclear properties I've presented to you are now constrained within an upper and lower bound limit and used in the calculation of the neutron-capture cross-section. This is the final step in using the Bethe-Oslo method. The plots illustrated here represent the neutron-capture cross-section as a function of neutron energy, where I've plotted Thales variations of theoretical models, what is currently available for strontium-93. What is currently available is essentially theory for nuclear level density and gamma strength function properties. Alongside this, I've plotted my work, which constrains the nuclear level density and gamma strength function to experimental data. You can see that the uncertainty band is decreased within this energy range. Similarly goes for the astrophysical rate. Here, the variations of Thales include, once again, models for the level density and gamma strength function, while my work represents the data-driven aspect of constraining the gamma ray strength function and nuclear level density. This is a powerful tool that can be used in regions where there is little nuclear data available so that we have a better perspective of the uncertainty based on experimental work. I'd like to conclude by thanking everyone at UC Berkeley as well as the national labs and expertise at Michigan State University that enabled me to perform this experiment. In addition, I'd like to thank those at University of Oslo who pioneered this method. Lastly, I'd like to end on a summary of my experience with the NSSC. I've had wonderful experiences at the Public Policy Nuclear Threats Bootcamp run by Dr. Bethany Goldblum, as well as the Exotic Beam Summer School that was held at Michigan State University. Lastly, I'd like to thank everyone at the national labs with my hours of in-residence research at Livermore National Lab and Lawrence Berkeley National Lab. With that, I would like to take any questions from the audience. Thank you.
Thank you, Adriana. Excellent talk. So you can go ahead and post your questions in the Q&A box now. We have one. What determined your constraint factors?
My constraint factors were determined based on the approaches I utilize, such as I've discussed that the neighboring nuclei that were available served as one of the variations on my normalization approach, but as well as investigating different microscopic models. So these are some of the constraints and finding which is the most lower bound component and upper bound component in a way sets the uncertainty band.
And so how does this vary from nuclei where you have experimental data available to help aid in constraints?
If nuclear data is available for this normalization, that would be ideal, and that would significantly decrease the uncertainty band. One of the first Bethe-Oslo experiments was for germanium-76, where external nuclear data was available. And in a way, this could be seen as a benchmarking of the Bethe-Oslo method, and that could be compared that indirect methods such as the Bethe-Oslo method could successfully produce results similar to those through a more direct method.
Adriana, another question. Andrea mentioned that one planned experiment at Argonne National Laboratory this summer may not happen in time for inclusion in your PhD thesis because you are planning to graduate this summer. Could you tell me a little bit about that experiment? My understanding is that you wrote a proposal. So what were you trying to accomplish?
Right. A key element to these indirect methods is that we're really trying to push the boundaries of our knowledge towards unstable nuclei. So the proposal I wrote was to perform similar beta Oslo measurements at Argonne National Lab using the Caribou fission source to measure or really determine the nuclear properties of strontium 94, 95, and 96. This is really pushing the boundaries so that we can extend our understanding of trends towards unstable nuclei. It would be a very large jump to believe that unstable nuclei and stable nuclei have the same properties and the trends that we can see there. So my experiment was scheduled for this summer, but due to the current climate, that wouldn't be possible. And I'm awaiting to hear how timelines will change for the future. My work still, regardless of this experiment occurring this summer, can propose some possible expectations of what we'd see in the unstable region, but best thing would be to have more nuclear data available.
Thank you so much.
Thank you.
So next up, we have Vincent Fischer from UC Davis. And we're switching topics now. Vincent is going to talk about neutron multiplicity and new technologies with Annie.
Okay, hello. I hope you can all see my screen. So, okay. So yeah, first of all, so hello, thank you. Thank you very much for giving me the opportunity to show you some of my research on neutron multiplicity and new technologies. And thank you all for listening to it today. So first, I'm Vincent Fischer. I'm a postdoc at UC Davis. My academic advisor is Professor Svoboda. My lab mentor is at Lawrence Livermore. It's Stephen Daisley. But I also worked a lot at Los Alamos with Dr. John Norman. So I worked at all those different labs. On the left, you can see some pictures of me. One of them is during one of our beam run at Los Alamos next to the dance detector. Another one is some work done at UC Davis. And another one is some work done at Fermilab. And so let me now talk about the relevance of this research to the mission of the NSA. And this relevance actually goes through the Watchman experiment. So Watchman is going to be a big detector, about 1 kiloton neutron detector for nuclear non-proliferation. It's going to be part of AIT, the Advanced Instrumentation Testbed. The idea of Watchman is that it's a US-UK collaboration. The detector is going to be built at the Boulby mine here, about 25 kilometers away from the Hartlepool power station with its 2 reactors. And the goal is to measure the neutrino flux from this power station, but then from remote reactors later through the inverse beta decay reaction, where a neutrino is going to interact with a proton, giving you 2 flashes of light in a detector from the positron and from the neutron. And Watchman is going to be using either of those 2 detection medium, either gadolinium-loaded water or water-based liquid scintillator or WBLS. And this is actually exactly where Annie comes in. So an overview of Annie. Annie is an experiment funded by the DOE Office of Science. Our lab partner is Lawrence Livermore National Lab. On the right, you can see a picture of the collaboration, and you can see 2 of our 2 other people at Livermore working on Annie, Stephen Daisley and Mark Benjamin. Annie stands for the Accelerator Neutrino-Neutron Interaction Experiment. It's a gadolinium-loaded water detector that is actually placed downstream of the booster beam at Fermilab. And the 2 goals of Annie, the primary goal is a physics goal, is to understand the final neutron multiplicity from neutrino interaction. And the second goal is more technological, is to actually demonstrate new technologies in both the fields of fast photosensors and new detection medium, and hopefully both of them combined. Annie has been taking physics data since the beginning of 2020 after a very successful background measurement that took place a few years before. And if you want more information about this background measurement, you can look at this paper here at the bottom left in the Journal of Instrumentation. So let's first talk about the physics goal of ANI. So as I mentioned, it was the study of the multiplicity of final state neutrons from neutron interaction on water. And so why do we want to do this? Well, if you look at high energy experiments, such as Dune, for example, to be very, to put it in a very simple terms, what those experiments want to look at after neutron interaction is those kind of interaction here on the right, on the top right. So when a neutrino is going to interact with a nucleus, here a neutron from the nucleus, creating a lepton, so a muon, and that's it. So this is a very simple interaction. You can look at the energy of all those final state particles here, and you can get the energy of the neutrino from those. But unfortunately, physics is not that easy, and nuclei are really not that easy. So what's happening in a nuclei can be a lot more complicated than this. You can have different processes from charge exchange to absorption and production of all the particles. And this would actually, yeah, as I said, create all the particles. And among those particles, you can find neutrons. So the presence of neutrons in those final states will tell you that something not expected happened, something not that simple as this happened. And that's what we call inelasticity. And the issue is that you have to send some energy to those neutrons to create them, which means that when you reconstruct your neutrino energy, you have a bias because you did not account for the energy of those neutrons. So you really have to understand this neutron yield. And since to do this, you need high statistics and very precise reconstruction, where you kind of need a dedicated experiment to do this. And this is where ANI comes in. And I said the second goal is a physics goal, technological goal. And this is mostly fast photosensors and new detection media. So in terms of fast photosensors, the detector that we're mostly going to be testing is called an LAPPD, or large area picosecond photodetector. So those detectors are microchannel plate based. They are 20 by 20 centimeters with about actually a very good time resolution compared to conventional PMTs, about 60 picoseconds. And that translates into a very good spatial resolution as well, less than a centimeter. And ANI will be the first use of this technology in an actual running experiment, not on a test bed. And this would actually quickly demonstrate that LAPPDs are not only ready for testing on test bed, but also ready for research and deployment as actual sensors for high energy physics, just the same as photomultiplier tubes right now. And in terms of new detection media, so I mentioned the two from Watchmen, and actually, even though this medium is it's not the first application of this medium, but ANI will be the first application of gadolinium-loaded water on a neutrino beam. And the other one is actually, as I mentioned, water-based liquid scintillator, or WBLS, and that's a mixture of both water and scintillator, and I'm going to go into more details in the next few slides. And so ANI would actually look at deploying this new medium in its detector. So speaking of the ANI detector, so I mentioned before that it was a gallium-loaded water detector. The volume is about 26 tons. This is our main central detector. It's instrumented with about 132 photomultiplier tubes and more than 5 LAPPDs. And why do I say more than 5? It's because we are starting with 5 LAPPDs. We have those 5 on hand, but as we go, we're going to increase the numbers as we buy more. But that's not it. ANI also has 2 sub-detectors. The first one is the front muon veto. So those are scintillator paddles placed in front of ANI between the beam and ANI. And the goal is to tag any kind of charged particles coming from the rock. And those particles will be coming from interaction in the rock. And you don't want to see those because you actually want to focus on interaction happening on the water. And the other one is also based on using plastic scintillators, but also with steel plates. And this is a segmented detector called the muon range detector, or MRD. And since it's segmented, it's actually capable of reconstructing the muon direction and its energy after the muons have been created in the water volume from a true interaction. And in terms of statistics, ANI expect about 10,000 charge current interaction per ton per year. So this is very high statistics compared to other experiments for a nominal beam running. So now, quickly, how would actually ANI work in terms of physics? So you start with a neutron interaction in your volume. You create a muon. This muon will create your anchor flights that you will detect with your PMTs and LAPPDs that will give you information about the momentum and the vertex of this interaction. This muon will also be reconstructed in the MRD. That will also give you some momentum information. Then you're going to create neutrons. Those neutrons are going to thermalize in the water, get captured on gadolinium, and you're going to see the lights from those captures on gadolinium using your photomultiplier tubes. And so now, the one slide with lots of nice pictures. This is how we actually build the detector. So most of it was built last year. The inner structure that's holding the photomultiplier tubes was assembled at Fermilab in about 8 to 9 months. the MRD, the mirror wave detector, was refurbished. Here you can see 2 NSSC fellows adding gadolinium into ANI. So on the right, it's myself. And on the left, this is Julie He, a graduate student at Davis. And we spent our Christmas and New Year's break last year adding gadolinium into ANI. Here you can see the ANI purification system, and I'm going to go into more details about this later. And here is a nice picture of ANI before we actually installed the last panel and then installed this into the tank. So to have this very precise experiment, you have to have a very good calibration. And ANI actually planned ahead and has several means of calibrating. The first one, we call it the LED calibration. So we have 6 fibers distributed all around the tank at different locations and connected to LEDs. The goal is to, well, the idea is to inject light from the LED into the fiber, and then you see this light using your PMTs in the tank. But the goal is to do some water transparency measurement by injecting always the same amount of light and trying to detect always the same amount of light. You can see if the water is going more or less transparent. Doing some PMT timing measurements and also some gain matching measurements. The other way to actually calibrate are sources. So we will deploy, or we actually deployed sources in ANI. We have 5 deployment ports on the top to actually deploy it at different locations in the tank. The main purpose here is to detect a tagged americium beryllium source. And the idea of americium beryllium is that it emits a gamma and a neutron. And if you can see this gamma, I mean, efficiently see this gamma, you expect a neutron right after. And this would actually allow you to do some neutron efficiency studies throughout the entire water volume, since you can deploy it using a wire at different height and different locations. And so what I want to mention here is that also this source, so this source that you can see here that's deployed here using this system that I made at Fermilab, the source was actually built in collaboration with Lawrence Livermore, because there's a strong interest from Watchmen to use this because, as I mentioned before, Watchmen is going to be a very similar detector. And actually they think about using either the same source or at least a very similar one to actually calibrate their detector. So a lot of this calibration work has been done in collaboration with Livermore. And also this actually includes some of the newer upgrades that we're going to do once the whole current situation is resolved, which is adding a laser ball for further PMT timing and a stand-on candle for detector stability. So now I said that I was going to mention the ANI water system. And so what I would like to start with is that all the large water Cherenkov detectors, including ANI, actually need to circulate and purify their water at all times to keep high levels of transparency, because you always have leaching from dust, from bacteria at all time. So there are existing systems, but they're quite big, they're quite expensive, and ANI could not afford neither the size nor the money. And so we developed our own low-cost purification system, and that was one of the tasks I was asked to do on ANI. And so the goal of this system is to remove impurities that includes dust, bacteria, dissolved plastics, and UV-absorbent ions like iron. And that's the tricky part, without removing gadolinium. It's easy to remove everything from water to make it pure water, but it's not that easy to remove only specific things without removing gadolinium, because gadolinium is actually quite easy to remove. So the idea here that I went with was to use conventional filters and sterilizing lamps to remove dust and bacteria, but then use another ultra filter, so a much finer filter, and a tuned ion exchange resin to actually remove all of it without removing gadolinium. And when I say tuned ion exchange resin, it's actually a resin that's commercially available, but that we prepared at Davis to actually make it impervious to gadolinium. And if you want more details, there is a study here that we published that has been accepted for publication in the Journal of Instrumentation, if you want to see more details about this method. This gave us very promising results on the test bed, but also in ANI. As you can see here on the right, this is the absorption and the function of the wavelengths in ANI. So the lower, the better, because the lower, the more transparent your water is. And as a function of time, the absorption just keeps on getting better using this whole system to purify the ANI water. And what's interesting to notice too is that this system could be actually used by small to medium scale detectors, including non-proliferation detectors that would be using gadolinium water as their detection medium, because it's a very compact and very low cost system. And all of this actually helped us get our first ANI physics event. So here is, you can see a picture here of this, this physics event here. All the 3 sub-detectors are shown here, and you can see that only the tank and the MRD were hit, which is exactly what we expect. We don't want any hits in the video because we don't want these particles to come from the rock. So this is a particle that was created in the water and ended up in the MRD, most likely a muon. As you can see here, this is kind of an exploded view of the inside of the detector. And you can see a very clear disc-like Cherenkov pattern, which further tells us that this looks like a muon. And here in the MRD, you can see And in blue, those are the panels that have been hit. You can see a straight track that was entry point correspond to the exit point in the tank. So this actually let us confirm that this event was actually one of the first neutrino events in Annie. So I mentioned water-based liquid theater. So let me go into more details about this on Annie. So there will be a talk about this tomorrow. So I won't go into too much details in this case, but the idea of water-based liquid theater, or WBLS, is that it's a mixture of water and liquid theater. And to hold them together, because they don't mix together by default, you use a surfactant that encloses the liquid theater in the micelle. This actually combines the advantages of both water, because of the low light attenuation, the low cost, and liquid theater for the high light yield. So it's very tunable, very attractive for low and high energy physics. And the fact that Annie is very modular, and a lot of our collaborators are experienced with WBLS, actually told us that those are key points that could make Annie a WBLS testbed. And so we are currently having discussions on possibly deploying a small vessel filled with WBLS in Annie this year. It was supposed to be this summer, but of course the current situation slows this down, but we're still discussing the possibility of deploying it this year. And this would make Annie the first detectors to use the WBLS as a detection medium on a beam. And this would be a very, very valuable input for the next generation of detectors that includes Watchman for non-proliferation, since Watchman plans on using WBLS as the medium, and also TEA, a much bigger next generation high energy physics detector. And as the last slide on WBLS, let me show you some of the R&D that's been done on it. And I'm going to mostly focus on the R&D that we do here at Davis. The first part is filtration and purification. We're applying nanofiltration to separate organics and water and then purify them separately. We have a setup at Davis, and we are in the process of building a bigger, better setup. We're doing some material compatibility study to make sure WBS is not damaging the materials and vice versa. So we have to screen all of the materials going into the water or into WBLS. We're doing some optical properties, and I think this is going to be the focus on the talk tomorrow about WBLS, but at Davis, we're constructing a 10-meter arm to actually look at the attenuation and the scattering lengths of WBLS, and we're doing some calorimetric properties where we measure the light yield of several cocktails of WBLS, and we look at the impact that different factors such as temperatures would have on it. So the conclusion, Annie started taking physics data. Annie will demonstrate, so the combined use of those new detection media and fast flow sensors, this would directly impact next generation of non-proliferation detectors such as Watchman. And what I want to end up on is that Annie and Watchman have very strong ties, both in terms of analysis, because we're looking at neutron captures, in terms of R&D with WBS, but also in terms of collaborators. In the collaboration pictures I showed you before, half the people actually were both on Annie and Watchman. So that's the end of my part of Annie. I'm going to quickly finish on my NSSC experience. So I presented results at the different program reviews of the NSSC in 2017-18, the full workshop in 2019, not only on this, but also on some beam runs that we've done at Los Alamos. Every year, UC Davis, as you heard this morning, hosts the NAT Summer School. And since 2016, since I started, I've been giving lecture there, and I've been in charge of the Neutron-Capture analysis that includes preparing samples, irradiating those samples at the reactor, counting them, and analyzing them. That was a very enriching experience. I actually like to teach students what we do in our everyday life, because some of the samples, I did them a few days before for another experiment. I also collaborated, this is a picture of us at Los Alamos, but on several occasions with experts at the Lance Neutron Beam. So that's at Los Alamos. We did 2 beam runs with them, and we also did follow-up studies. And this actually helped me develop a lot of skills in detector design, low background assay, background mitigation. And I would very much like to continue to apply those skills to further continue working for the NNSA mission at a national lab. And with this, I thank you. I thank the NSSC for its support, and I thank you all for listening to my talk. And I'm ready to take any questions. Thank you.
Thank you, Vincent. It's an excellent talk. So I have some questions. So what is the primary background for Watchman? Hold on, I'm getting feedback.
Sorry, let me mute maybe.
So what is the primary background for Watchman-like detectors for reactor antineutrino monitoring?
Okay, So there are several, because here Watchman, unlike Annie is looking at high energy events. Watchman is looking at low energy events because they're looking at those reactor neutrinos. Backgrounds are numerous. You have random radioactivity background coming from the outside or even the inside with uranium, thorium in your water. You have some backgrounds actually coming from cosmic rays. Either that directly, a muon would just hit your detector, give you some light, or indirectly, where a muon would create radioactive elements, and those elements maybe 30 seconds later would decay, and this would give you actually something that looks like a neutrino event. You're also looking at some, again, coming from cosmic rays, but some neutrons created by muon spallation outside your detector that would enter your detector and give you a coincidence signal. So the backgrounds are numerous, so that's why people need to do, lots of people are doing lots of simulation to make sure that those are understood, and if they, and they are mitigated by using vetoes or different kind of analysis techniques.
Thank you. And another question, how will you measure the water-based liquid scintillator light yield?
So at the moment at Davis, and I know that other universities have their own device, but we had a device that was made with also another NSSC fellow, Leon Picard, another postdoc at UC Davis, that you can see here on the right. Basically here you have a very small quad cell that you fill with liquid scintillator, and we have 8 PMTs looking at it, and we put a radioactive source on top of it. So basically the particles from the source are going to hit the WBS, give you some of the light yield, and this is how you would measure it. And so the idea was to measure the light yield using this machine quite quickly after doing all of the tests that we've done here. For example, you look at some WBS that has been filtrated before, and you look at it after, and you want to see if that impacted the light yield or not. And I know that some other universities also have some other methods, maybe with bigger cells, that could actually use other kind of particles or have a better measurement, have a more precise measurement. But this one was kind of designed to be a faster way to measure it right after doing those tests.
Thank you so much. If there's no further questions, I'm going to thank Vincent again, and we'll transition to our next talk.
All right, thank you very much.
So next up, we have Katherine Childers from Michigan State University. She's also going to be talking about the Bethe-Oslo method, but in this case, validation of the method for constraining neutron capture cross-sections. Katherine.
Thank you. Let me go ahead and get my PowerPoint going here. All right, so thank you, everybody, for being here this morning or afternoon and joining us for this Virtual Scholar Showcase. I'm going to be discussing some of the work that I've done towards validating an indirect method we use for constraining neutron capture cross-sections. Sorry. And so just a little bit about me. My name is Katherine Childers, and I am going into my 6th year of grad school at Michigan State University within the Department of Chemistry. I also work at the National Superconducting Cyclotron Laboratory located at MSU. My academic advisor is Dr. Sean Liddick at MSU, and my laboratory mentor is Dr. Aaron Couture out at Los Alamos within the P27 division. And so I do apologize if a little bit of this is repetitive from some of the previous talks. I'll try not to go into too much detail. If you are joining just now, I would encourage you to check out the slides of Andrea Richard and Adriana Sweet. They have some great information in their talks as well about this method. But just to talk quickly about why we care about neutron capture cross-sections and how we can measure them. These cross-sections are really valuable for a large variety of nuclear data applications, from applied things such as nuclear energy, non-proliferation, reaction networks, and also more basic science such as future discoveries in astrophysics. A lot of these cross-sections that are needed for these applications are not well known currently. And this is because we are unable to do direct measurements on these, a lot of these that are short-lived, farther from stability, because we can't use a radioactive target and we can't use a neutron target either. So a lot of indirect techniques have been developed. Many of these are using a statistical model, such as Hauser-Feshbach. We can use theoretically calculated nuclear properties within these models to determine cross-sections. Unfortunately, a lot of this theory also comes with its own challenges. So this is an example here on the left of strontium-95 N-gamma with the cross-section as a function of energy. And each of these bands is the cross-section calculated using TALIS with various combinations of all the theoretical models for all these nuclear properties that go into this calculation. And you can see that this is approximately an order of magnitude. And so this large range of possible cross-section ends up introducing a large uncertainty. And so to show a quick example of this impact on an astrophysical calculation of abundance patterns, here we have a study done by Liddick et al. These black dots represent a solar abundance pattern, and then all of these green bands represent a calculated abundance pattern using neutron-capture cross-sections of varying uncertainties. And so you can see that with an uncertainty of approximately 100, shown by this lighter green band here, it's really hard to identify a lot of the features of this plot. And so if someone is trying to decide whether or not this model fits the known abundance pattern, that could be quite difficult. But as we better constrain the cross-section to a factor of 10 or even a factor of 2, shown by this darker green band, these features become a lot more apparent, and it's easier to determine whether or not this is a good fit. So there are a lot of indirect techniques to experimentally constrain these inputs. The one that I'm going to be talking about that we use at MSU is the Bethe-Oslo method. So with this method, we populate the higher excited states of the compound nucleus of our reaction of interest using beta decay, and they measure the subsequent gamma decay. And with this, if we're using a high efficiency detector, we can obtain both the individual gamma ray energies and the total excitation energy of the nucleus. And using this measurement, we can then extract properties that are used in the calculation of the cross-section, like the nuclear level density and the gamma ray strength function. And so then these extracted properties are inserted to experimentally constrain those cross-sections. So this method has been used. You've seen a couple talks about this already. This method has been used already for quite a few cross-sections, and it's been benchmarked against the original Oslo method, which has been around for a while, and also benchmarked with a titanium-50 direct measurement. But we want to be able to validate in a higher mass region to make sure that the assumptions we're making still hold true at higher mass. And so we chose the selenium-82 N-gamma reaction. This produces selenium-83 via neutron capture. Selenium-83 is also produced via the beta decay of arsenic-83. And both of these reactions are able to be studied in a laboratory setting. And so these, I'll be talking about experiments for both of these now. So first, I'll talk about the experiment we did to study the beta decay of arsenic-83 at the National Superconducting Cyclotron Lab. We had a krypton-86 primary beam accelerated via our couple cyclotron facility, impinged on a beryllium-9 target, and then an arsenic-83 secondary beam was delivered to our experimental end station. It was implanted into a silicon double-sided strip detector located in the center of SUN. So you might have heard a little bit about SUN earlier, but SUN is the summing sodium iodide detector. It is a segmented detector, and so we're able to obtain the individual gamma ray energies using the segments, or we can sum the total detector volume to determine the total excitation energy of the nucleus. So these are the various steps of the Bethe-Oslo method. So this is our raw, what we call the raw 2D matrix of the excitation energy as a function of the gamma ray energy. This raw matrix is then unfolded in order to take into account the detector response. The unfolded matrix is then used to determine the primary gamma rays, or initial gamma rays that come out from each cascade. And from the primary gamma ray matrix, in the statistical region, we can extract the nuclear level density and the gamma ray strength function. So both of these values need to be normalized. And so for the nuclear level density, this is the level density obtained for cesium-83. We normalize to known energy levels at lower energies, and at higher energy, we can normalize using the level density at the neutron separation energy determined through known nuclear data from Ripple with a constant temperature model extrapolation. Since we are using beta decay, we do have to take into account that there is a reduction. There is a reduction of the level density from the restricted spin population. And so this is the spins and the percentage of the level density as a function of the spins. This is the spin range that is populated through this reaction. So this accounts for about 50% of the total spin range. And I can use that to then reduce the level density from the previous slide. This is my gamma ray strength function normalization. So normally this would be normalized using the average radiative width, or gamma gamma, from Ripple, but of course that was not reported for this nucleus. So I used photoabsorption data obtained from a couple nearby nuclei to extrapolate the giant dipole resonance down to lower energies, since the strength function is the tail of the giant dipole. And then I used that to determine the optimal gamma gamma value for my data. And so this is the strength function with its upper and lower limits that I obtained. These values are then used in TALIS to calculate the cross-section for this reaction. So here I have shown the cross-section I have obtained with its upper and lower limits. I've also included a couple direct measurements that have been made over the years, but since some of these are only single point measurements, they don't necessarily agree with each other, we wanted to be able to do our own direct measurement across a larger energy range in order to compare this. And so we headed out to Los Alamos National Lab, to the Neutron Science Center, where we used the detector for advanced neutron capture experiments, or DANCE, which is a large gamma ray calorimeter with 160 barium fluoride crystals. So a target is placed in the center of DANCE and then impinged with a neutron beam. This neutron beam is produced with a proton beam that's produced from their linear accelerator, which is then impinged on a tungsten target, creating beams of neutrons that are moderated down their various flight paths. And so DANCE is located here at flight path 14, which is approximately 20 meters long. So this is some of the raw data from DANCE. This is the neutron energy here on the x-axis. This is determined via time of flight. And the total energy observed in DANCE, or E-sum, on the y-axis. And so the total energy is related to the Q value of the reaction. And so you can see a lot of resonances pretty clearly in this plot, and you can also see that they're all, at various total energies, various Q values, and that's indicative of several contaminants in the beam. And so these selenium-82 resonances are down here. And so in order to clean this plot up a little bit, we first need to take into account the scattering background. So any neutrons that might scatter off the target and capture in the barium of the crystals. And so we use a lead target in order to account for this. That is subtracted out of this bin by bin. And we're left with something a little bit cleaner. So the next step I need to take is to account for all of these various contaminants. So these are other stable selenium isotopes that, even in very small amounts in my target, some of the resonances do show up in my spectrum. And so selenium-82 has the lowest Q value. And so just putting a Q value gate doesn't totally take care of this, because the tails of the resonances will still show up in this Q value gate. And so I did a stepwise subtraction. starting with the highest Q-value isotope and subtracting its contribution from each following Q-value gate until I ended up with just the yield of neutron capture on selenium-82. So this worked pretty nicely. There is a small over subtraction here. We don't yet have a great answer for what that's attributed to, but we will be looking into that a little bit more before publishing final results. So from here, there's still several other steps to get to a cross-section, taking into account things such as the detector efficiency. All of these steps are things that I'm currently working on. So I'll leave you with this today, and hopefully I'll have everything else finished up very soon. So just in summary, the beta-Oslo method needs to be validated against a directly measured neutron capture cross-section. The level density and strength function for selenium-83 have been constrained using the Oslo method, which was then used in Talus to constrain the cross-section of selenium-82 and gamma reaction. And this will ultimately be compared to a directly measured cross-section with DANCE. And that analysis will be finished up very soon. I'd like to thank all of my collaborators who have given an immense amount of help, both for experiments at the NSCL, experiments out at Lance, and all of the support I've gotten for analysis. I'd also like to take a minute to discuss my NSSC experience. So I've only been in the NSSC for about a year now, but I have had the opportunity to take several trips funded through them. One was I went out to PNNL for their Radiation Detection for Nuclear Security Summer School, which was a really great experience. If there's any other students on, I really encourage you to look into that because it's a really great school, 2 weeks, and you learn a lot of things, and it really helped me to determine that nuclear security was something that I want to continue supporting with my next steps of my career. I was also able to go to the NSSC Fall Workshop and Advisory Board Committee out at Lawrence Livermore. And this was also a great event, a lot of networking opportunities. I've been to the, presented at the APS DNP this past October in Washington, DC. And I've also made a lot of trips out to Los Alamos National Lab to work with Aaron Couture and the dance group. And even now back in East Lansing, I've continued closely collaborating with them remotely. And with that, I would like to thank the NSSC for all of my funding and for giving me the opportunity to speak today. This has been a really great experience. And thank you for all of your attention.
Thank you, Katherine. Do we have any questions from the audience? So can you remind us, Katherine, of the detector efficiency?
For what? For sun or for dance?
Hold on, we're waiting for interaction from our participants here. Both.
So the efficiency for dance, I cannot comment on yet. That is something that I'm currently gearing up to do quite a few simulations with Dicebox and J.on in order to determine that efficiency, since that affects the cross-section. For sun, of course, I cannot remember the efficiency right off the top of my head. I think maybe Andrea had that on one of her slides. She had a slide with a little more information on sun.
Andrea, if you're here, you can also type into the Q&A. Okay, thanks again, Katherine. So if we have no further questions, we're going to go now to a break, and we'll be back at 10:50. Before folks run off, I would like to go through, and for those of you that haven't identified yourself with your first and last name, we just like to go through and validate the attendee list here. So because the chat is disabled, you're going to need to comment in the Q&A box. And I'm also in the chat going to type in the email address, or Charlotte's going to type in the email address where you can reach her to provide your coordinates if you can't use the Q&A box. So we have one phone dial-in person. I think you're going to need to email Charlotte. Presumably you can't use the chat box. So please email Charlotte with your first and last name. The phone number is 925-337-9963.
Just to mention, if you haven't seen, Andrea did answer because she was muted, so she typed in, it is 85% at 1 MeV.
Thank you. Okay, and we also have someone named Hannah. Hannah, can you email Charlotte with your first and last name or type into the question and answer box? We have a Jacob. We have an owner and a Micah. So thank you, Hannah. If we can't get these folks identified, we're going to be removing you from the virtual meeting. Hi, Ahmed. It's nice to see you. Thanks for the communication. So we'll be doing that before 10:50. So please communicate with Charlotte or type into the chat, hi, Jacob, over the next few minutes. And thanks for joining us, Eric Brubaker as well. Okay, so we'll be back at 10:50. Thank you. Hi, welcome back to the last segment of the NSSC Virtual Scholar Showcase. We're going to hear two more presentations from our nuclear and particle physics focus area, and then we're going to close with one from our nuclear policy cross-cutting area. So first up, we have Eric Matthews, who is a graduate student at UC Berkeley, and he's going to be talking about independent and cumulative fission yield covariance matrices for 61 compound systems. Take it away, Eric.
Thanks, Bethany. Let's see. Okay. All right, hello everyone. So I'll be presenting today on a method for generating independent and cumulative fission yield covariance matrices for 61 compound systems. Okay, so a little bit about me. I'm an NSSC fellow. I also was an undergraduate researcher at the NSSC when I was an undergrad at UC Berkeley. My collaborators span several national labs. Dr. Lee Bernstein at LBNL is my main lab advisor. I've also worked with Dr. Goldblum, Dr. Walid Younes, who is now at LBNL, but was previously at Livermore, Josh Brown, and John C. Batchelder up at LBNL. I am currently an affiliate, an academic program affiliate under Joe Ressler at Livermore. And I also work with Dr. Anton Tonchev and Dr. Jack Solano on fission yield measurements. And I've been collaborating with Denise Neudecker and Toshiko Kawano at Los Alamos on a template on fission yield uncertainties. And then finally, I've been working with Dr. Bruce Pearson in relation to my fission yield work at Livermore and Berkeley Lab. So to give you a little bit of motivation for what I'm going to present today, in 1994, England and Ryder did a comprehensive fission yield evaluation. This was the last complete fission yield evaluation for the US Nuclear Data Program, but that evaluation didn't include information on covariances between fission yields. Having these covariances would be important to a number of applications. This can include forensics and safeguards calculations. One very hot topic right now is reactor antineutrino rates, and it's also been identified as important for decay heat calculations, reactor inventory, and poisoning. So there's been some previous work done to generate these covariances that can be used for applications. There was a large body of work that came out of WPEC subgroup 37, which focused on this. That included work by Pigne, Schmidt, and Leray. And then there was also work done by Kawano and Chadwick in 2013 on this. The work by Pigne, Schmidt, and Kawano was at WPEC subgroup 37. And the work by Pigne, Schmidt, and Leray relies on some underlying model of fission to generate these covariances. That means that you rely on the parameters. You can only use those methods where you have parameters for your given compound nucleus, which is much narrower of a range than the compound systems that exist in NDEF. And none of these results are publicly available, largely because they're not readily accessible through the NDEF format. So the motivation of this work is to generate a set of covariance matrices for the England and Ryder evaluation with as little fission model bias uncertainty as possible. And this method will follow simple conservation rules in order to constrain a sample space for Monte Carlo bootstrapping. This covariance matrix will predominantly reflect the evaluated uncertainties in the independent fission yields rather than reflecting the model parameters that are used in model-dependent generation methods. And now that these matrices have been generated, they're publicly available online, which I'll give a link to that at the end of this presentation. So to kind of start us off on what is going to be done, we're going to be using a Monte Carlo uncertainty method to generate these covariance matrices. If you have a data set with characterized uncertainty, you can build a new series of data sets by resampling the original one about its uncertainty. This is commonly used to do forward propagation of uncertainty, where you take your data set and run it through a calculation, and then you re-perform that calculation with a varied input set. But this can also be done to assess covariances between values in the original data set if you have some knowledge about how those quantities will vary with each other. So an example of this is the yield of xenon-138, which I've shown here. The black line on this figure represents its evaluated yield, and the red bands represent its evaluated uncertainty. We can resample this 100,000 times about a Gaussian distribution, and this is what you'll get. So that's an example of Monte Carlo. However, if we were to just go through and do this for every single fission yield independently of each other, we wouldn't see any correlation or covariance. So we have to establish some way of keeping relationships between all of the fission products. So in order to do that, we're going to use some conserved quantities and enforce them on each of the resampled sets of data. There are 5 relationships that we'll use. Total yield, because each fission produces at least 2 binary products, all of the binary yields should sum to 2. Total charge, if you multiply each yield by the Z of that particular product, you should recover the total charge of the compound nucleus. Total mass, if you multiply each yield by the mass of the product, you should recover the mass of the compound nucleus less your average neutron multiplicity, because that mass is lost from the fragments. And charge parity, this one is a little more subtle. That is that if you take all of the yields to products with a given Z, Z1, and sum them up, they should be equal to the sum of all yields of complementary products, complementary being products with Z of the compound nucleus minus that Z1. This is, if you think about this in the fission process, when you get a fission, pair fission fragments, the yield to those fragments needs to be the same, and this is what conserves that. Finally, there's a mass symmetry condition. This was originally proposed by Fiorotto. There should be some point in the fission product distribution that you can identify where the yields on one side are equal to 1 and the yields on the other side are equal to 1. This relationship is only approximately conserved. It nevertheless can be exploited to conserve these other 5 relationships. In particular, what we do different than Fiorotto is Fiorotto proposed this, picking a midpoint of your average neutron multiplicity subtracted from your compound nucleus divided by 2 is where your midpoint should be. And that's approximately true, but in this method, we actually go in and find numerically where that midpoint exists exactly. Okay, so we want to preserve those 5 relationships. So we come up with some structured way that you can resample the fission yield such that you're doing that. And so I'm going to go through those steps now. First, you randomly select whether you're going to resample the light or heavy side of the fission product spectrum. And then once you've selected that side, you go into that side and you randomly select a product in each A chain, and you resample it, that selected product, about its evaluated uncertainty. And then you rescale all of the other yields in that A chain by the same % change. The reason that we do this is the Z distribution of a given A in the England and Ryder evaluation was set to be a Gaussian. We know that also empirically that is expected to be true. So this preserves the correlations that should be expected from the England and Ryder evaluation. Then we take P of new data and we use that to generate the fission yields on the complementary side of the fission product spectrum. So the yield, the fractional yield to any product on the other side from a product on the side that you resampled should be equal to the yield of that product times the neutron multiplicity for a given nu. So once you have these fractional yields, you can sum them all up to get the yield to a complementary product on the other side of the fission product spectrum. So by step 5, we've ensured that we've met all of the conservation rules. Step 6, you repeat this process n number of times and you select a very large n such that your statistical noise is minimized. In the matrices that we calculate, we do this 10,000 times, and then you calculate the resulting correlation matrix. So here I show a resulting correlation matrix that would be produced from this method for fast fission of uranium-235. So as you can imagine, this method relies heavily on the accuracy of your P of new data. And the England and Ryder evaluation doesn't make any mention of the neutron multiplicity distribution used in their evaluations. And so we have to come up with some set of values. Here I show P of nu for fast fission of uranium-235. It is assumed that P of nu is the same for any emission of any set of fragments. But in reality, we know that that's not true. P of nu has dependence on A, Z, energy, etc. One of the most common formulations, or one of the most common ways of expressing this complexity is through P of nu of A distributions. These have been experimentally measured a limited number of times. So what we're going to do is assemble an England and Ryder consistent set of P of nu of A data. So a truncated Gaussian is used to fit the shape of P of nu for each A chain. And you select a P of nu that minimizes chi-squared between evaluated yields and so-called recalculated yields. Your recalculated yields use the same equation that we use to generate the fractional yields. Your recalculated yield should be equal to the sum of all of the fractional yields that are seen through P of nu of A. When we do this, we get a figure like this. The blue dots are the evaluated yields, and the red dots are the recalculated yields using the P of nu of A that minimizes the difference between these red dots and the blue dots. And you can see that for our high statistics yields in the evaluation, we get decent agreement. There is, of course, though, a discrepancy between several of these that you can still see. And this is actually a known problem. A paper published by Jafke in 2017 identified the issue that evaluated yields are not consistent with neutron multiplicity data. This is just a nuclear data issue that would require a joint evaluation of those two quantities in the future. And to kind of drive home this point of what this does to our data, we can look at the resampled yields for an example nucleus. Here we're using tellurium-132. When you use a simple P of nu data versus this England and Ryder consistent P of nu of A data. So in the case where we use the simple P of nu data, you see that when you resample the yields, you get two distributions within your resampled yields. One results from when you pick the heavy side of the fission fragment distribution to resample from. That's where tellurium-132 is, and you see you get a Gaussian shape that's centered about its evaluated yield and has width of approximately its evaluated uncertainty. And then you see a second Gaussian distribution, much wider. That results from when you pick the light side and you're calculating the yield to tellurium-132 using this simple and inaccurate P of nu data. When you use this consistent P of nu of A data that's generated, you see that the distribution comes closer together. You're not going to get perfect agreement with the mean and the width because, again, P of nu of A data isn't consistent with fission yields. And until that nuclear data issue is fixed, you're not going to be able to see that. But nevertheless, there is a significant improvement. The mean of that distribution is much closer to the expected evaluated yield, and the width is much narrower than the width of the bimodal distribution obtained using P of nu data. And so we can take some data from this covariance and correlation matrix and look at a particular slice of it to see some expected physics. So here we're going to look at the covariance between tellurium-132 and all of the other fission products in this distribution. So first of all, we see that tellurium-135 is positively correlated with itself. That's a good thing. If it wasn't, this method doesn't work. Products along the A chain that tellurium-135 exists in have a positive correlation. That's expected because we enforced a Gaussian distribution in each A chain, and that's what the England and Ryder evaluation did. We see that this correlation is reflected along a complementary A equals 99 chain, and we expect to see it there because nu bar of fast fission of 235 is about 2. So we should see the strongest positive correlation along A99, which if you do 99 plus 2 plus 135 gives you 136, the compound mass of the nucleus. And finally, products along A chains do not have complementary, products along A chains that do not have complementary Z have negative correlation. And the reason that we expect to see this is to conserve the normalization of the neutron multiplicity distribution. If one particular product in the neutron multiplicity distribution gets a boost, all the others need to go down in order to conserve a normalization of 1. So good, we see expected behavior. In conclusion, this method provides a model agnostic way of generating covariance matrices for fission yields. This has been successfully applied to all 61 compound systems in the England and Ryder evaluation, both for independent and cumulative yields. The results demonstrate expected behavior and trends. These final results will serve as an interim solution for using covariance matrices for fission yields until a new evaluation is completed, and that new evaluation, which is currently going on at Los Alamos National Lab, led by Toshihiko Kawano, will include a full covariance treatment. The results of this are publicly available online at nucleardata.berkeley.edu. It's the first time that these yields have been made available publicly, these covariances have been made available publicly. And it's also the first time that covariance matrices have been generated for this broad of a set of compound systems. And finally, a peer review publication has been submitted on this method. It was submitted to Physical Review C. It has made it past the editors and is currently with referees. With that, I'd like to talk a little bit about my NSSC experience. I have been given the great opportunity to share my work with the community at several of the NSSC's organized events. In 2017, I was a student in the NSSC-sponsored nuclear security course at the Goldman School here at Berkeley. And in 2019, I got to be the GSI. And I've gotten to interact with the national labs in a number of different ways through research, but also through the NSSC's workshops and summer schools. Here I'm pictured at the Lanel SNL summer school in 2015. It's been a very enriching experience. And this experience has given me a leg up when applying for other fellowships, such as the National Nuclear Security Administration Graduate Fellowship, which I completed last year. So with that, I'd like to thank the NSSC and take any questions.
Great job. Excellent talk, Eric. So a question from Ahmed, is the somewhat non-Gaussian shape of the consistent set due to the multiplicity issue that you mentioned?
Yes, this is due to the multiplicity issue. So to kind of point it out, for example, if tellurium-132, if we look at this A equals 135 chain, you see some of these yields, even when we do this chi-square minimization to get this consistent P of nu of A data, we can't get all of the data points to overlap completely. So there is some discrepancy due to this inconsistency between the P of nu data and the fission yield data. So that ends up being reflected here as you still see a little bit of a bimodality. It's improved by this P of nu of data, where instead of having this huge gap that we do with a simple choice of P of nu, we get a much closer agreement. But yes, that is caused by the inconsistency between the P of nu of A data.
Are you also using this P of nu of A data in other applications?
No, I wouldn't recommend it. So in the publication that we've sent forward, that is discouraged. So if you were to plot like nu bar of A, we do see expected trends that match experimental data. But because this is being used to tune fission yields to be most consistent with the evaluation, it's somewhat of an artificial set of data. So I don't recommend its use in other applications.
Thank you. Thank you so much, Eric.
Thanks.
Okay, next up we have Reddie from Michigan State University, and he's going to be talking about upgrades for an improved measurement of the electric dipole moment of radium-225.
Thank you, Bethany. Sharing my screen. Thank you for the opportunity to talk about my work. My name is Reddie. I'm a graduate student at Michigan State University, and I'm going to talk about my work recently on a search for electric dipole moment using the isotope radium-225. So my work on the radium project involves a lot of high voltage development and laser spectroscopy for various upgrades to the experimental apparatus. But last year I also worked at Livermore for my NSSC practicum with Nick Schilzo's group. So for this talk, I'll focus on my recent work on the radium project, and then I'll tie that back into the practicum work that I did. So if matter and antimatter were treated the same way, presumably in the beginning of the universe, all the matter would annihilate with all the antimatter, and we wouldn't be here having this great workshop today. But thankfully, that's not the case. There's some mechanism that allows matter to dominate the universe, and that mechanism is the rare violation of the combined charge and parity symmetry. It's also known as CP violation. The observation of a non-zero electric dipole moment would be a new clean signature of a CP violating process. So EDMs are expressed in terms of the electron charge times centimeters for historical reasons. In the upper left, I have the Hamiltonian for an atomic system with an electric dipole moment term. There's also the magnetic dipole moment term, which couples to the magnetic field and is easily observable and conserves CP. You can see the electric dipole moment, which is the D term, couples to the electric field. So it's kind of analogous, but of course it violates CP. And if we look at the cartoon I have at the bottom of the slide, with the both the electric and magnetic dipole moments initially aligned along the spin axis, as I apply transformations to the system, the electric dipole moment behaves differently under those symmetry transformations. So this is the radium apparatus. Starting from the left, we have our oven. So we heat up our atoms and they shoot out of a nozzle. We then collimate them, slow them, and trap them with lasers. We have to use lasers because the vapor pressure of radium-225 is very low. And then we bring them over to a shielded environment where we apply a low uniform magnetic field, and we generate a very high stable electric field with a pair of electrodes, which is at the right of the schematic that I'm showing. So when the atoms are between the electrodes, they'll be in the presence of magnetic and electric fields, and they'll learn more precise about the fields. We measure the frequency of the atoms with two configurations, with the electric fields aligned with the magnetic field and anti-aligned with the magnetic field. That gives us two expressions for their frequency, which we can use to solve for the change in frequency due to the EDM coupling to the electric field. So you can see this precession frequency change equation in the upper right of the slide. If the electric field is really, really, really high, and the change in the magnetic field is really, really, really low, then we can isolate the precession frequency change due to the EDM. So now I'll talk about the work I did on improving the electric field magnitude that we apply across the atoms. This is a little snapshot of what they look like. This is a pair of niobium electrodes, and they're like an inch in dimension. They would fit in the palm of your hand. So I test a lot of electrodes. I have 8 pairs of electrodes, and more are being machined. the first thing after we machine them and mechanically polish the electrodes and chemically polish the electrodes, the first thing I do is I high pressure rinse all of the electrodes with ultra pure water in a clean room to keep the electrodes free of any particulates. After rinsing them, I only ever expose them to environments that are clean room environments that I validate to class 100 or better. So I spent a lot of time in clean rooms, and I've installed electrodes in various systems at different labs, and I've actually had to build a few clean rooms to ensure that our electrodes and the vacuum chambers that they're installed in stay clean. I also built a high voltage test station for testing the electrodes, and there's a lot of information in this schematic. I'm just going to pick out 3 things that I think are important. So whenever we do an electrode swap for testing, or whenever we upgrade some part of our test station, we have to turn the pumps off, which could be an issue in terms of keeping the chamber clean. But what we do is we can slightly pressurize our chamber with dry nitrogen, and we send that dry nitrogen through a high volume 0.2 micron particle filter to keep the chamber clean. I test all the electrodes with a 30 kilovolt bipolar, so positive and negative polarity power supply. It's a super low noise device with a max ripple of 10 parts per million at full load. And I measure all the current flowing between the electrodes with a very sensitive picoammeter. It's accurate to within 2 picoamps or so. So after we polish our electrodes and clean them, we do an additional polishing process. And this process is called high voltage conditioning. And the idea is you use controlled low magnitude discharges between your electrodes to ablate imperfections on your high gradient surfaces. So it's kind of like polishing your surface by melting away any points or emitters. So this plot is a plot of the average discharge rate between the electrodes over time as we condition the electrodes. And this is for a 1 millimeter gap size. So we start at 12 kilovolts or 12 kilovolts per millimeter. As we increase the voltage, you can see that the discharge rate generally increases as well. But the trick to high voltage conditioning is you increase that voltage slowly, and you wait for some number of hours until the discharge rate drops to some steady state value, and then you can increase your voltage again and do the whole thing over. So for this pair of electrodes, we went from 12 kilovolts per millimeter to 20 kilovolts per millimeter. Somewhere in our 19 kilovolt high voltage conditioning shift, we polished away some large source of discharge activity, and you can see the discharge rate actually plummets to a lower discharge rate than when we first started conditioning. So at 20 kilovolts per millimeter, after 30 hours of conditioning, the discharge rate was actually lower than when we started at 12 kilovolts per millimeter. So I'm in the final stages of writing a paper on this work, and it'll be published in the near future. We're also concerned about possible systematics in our EDM measurement due to misalignments between the electrodes. So what I also did was I built a model of the electrodes in COMSOL, which is a finite element analysis software. And I looked at how the electric field behaved in the region of the gap where the atoms would be as we introduced misalignments. So I chose a large angle between the electrode surfaces, and I chose a large horizontal offset between them to see how the electric field angle would change as we scan from the top electrode to the bottom electrode. And the good news is, even for large misalignments, which are larger than what we would typically use in an EDM measurement, the electrodes behave like they're infinite planes from the point of view of the atoms. So this informs our modeling of this leading systematic. Now I'll just briefly hop over to the work I did at Livermore. This was part of my NSSC practicum from January to March of last year. And what I did was I worked on a fission product yield estimate project. So you have some decay chain and your longer lived fission isotopes with half-lives of hours to days. Some of those isotopes have relatively large uncertainties on the intensity of the gamma rays they emit as they beta decay to stability. And this affects the uncertainty in the fission product yield estimate. So the goal of the project was to develop a new a method of measuring some of these long-lived fission isotopes to sub% precision. So at Livermore, they assembled a new high-purity germanium gamma ray detection system in late 2018. I joined the project in early 2019, and the first thing I did was I built a model of the new detector system in GEONT4. Then we took 10 standardized gamma sources and measured them with the new detectors. That's on the left, and we got the efficiency versus the energy of the gamma ray. It's about a 2.5 MeV range. I then simulated the efficiencies for those energies and compared the measured data to the simulated data, which is the plot on the right. And after only a few months of calibrating and refining the GEONT4 model, we were accurate. The model was accurate to within an average of 3%, which is pretty good for a few months of work. And I believe the one major reason that we were able to do so much work in such a small amount of time is the work I did on the radium project helped me develop a skill set that had a lot of overlap with the fission product yield project. So I would say my experience with the NSSC has been very positive. I got to be exposed to a lot of research that I otherwise would not have been exposed to. I met great people at Livermore, and I discovered that my favorite kind of research to do is gamma ray spectroscopy. So I'm very grateful for that. And I am graduating in the early fall, so I'm now looking for postdoc positions at national labs in gamma ray spectroscopy as a result of my practicum. So I just want to briefly thank the small army it took to make the high voltage development for the radium project go smoothly. Lots of undergrads were needed for this. And I'd also like to thank the NSSC, and I'm happy to take your questions. Thank you.
Thank you, Roy. Do we have any questions from the audience? So Roy, I was interested to see how your work at MSU tied in with the work that you did at Lawrence Livermore. Can you talk a little bit more about that?
Yeah. So a lot of the data analysis work that I did on the fission product yield project used the same. It was a root analysis, which I had been familiar with my work on the radium project. Also, working with Giant4, this was relatively new for me coming into the Livermore project, but I had gained some familiarity with modeling detector systems on the Radium project, working with COMSOL. And the Livermore project is a precision measurement of gamma ray intensity. It's a sub% precision measurement, and the EDM work is very much a tabletop precision measurement, since the quantity is, since the EDM has never been observed before. It's a very precise measurement, so the style of the work was very similar.
Great, thank you so much.
Thank you.
And I want to remind everyone on the call that these students are looking for positions at the labs. Their CVs are available on the event website, which the URL is available in the chat, so you can check that out. You can reach out to these students directly. You can also contact Charlotte and she can connect you with them. And so we're going to be moving now to our final talk for this session. Today was mostly nuclear and particle physics. We're going to have some nuclear policy, and then tomorrow we're going to be looking at nuclear chemistry and radiation detection and nuclear instrumentation. So to close us out for today, we have Dr. Andrew Reddie from UC Berkeley, who's going to talk about experimental wargaming at the nuclear threshold.
Perfect. Thanks, Bethany. Hopefully my slides are up there for everybody to see. I am Andrew Reddie, a postdoc at UC Berkeley, at least for another few days. Thank you to Dr. Goldblum, Professor Vujic, and everybody for joining the call this afternoon. Excited to share research findings from our experimental wargaming project that some of you may have already kind of come into contact with at UPR and the Fall Showcase. So given that I've presented this a few times, I'm going to try to really focus on showing you some new material that we have on our preliminary results here in this presentation. As Bethany mentioned, I'm a postdoc at UC Berkeley. This project is directed at UC Berkeley by Dr. Goldblum and is done in concert with the Center for Global Security Research at Lawrence Livermore National Lab, where my mentor was Wes Spain, and with Sandia National Laboratories, where my mentor is Dr. Jason Reinhardt. The project itself is sponsored by the Carnegie Corporation of New York, and the project name is Project on Nuclear Gaming, or POM. And during this project, we've done a lot of different work across the labs, and very thankful for their support as we kind of run through this. With that said, at the outset, it's important to note that I speak for myself, and that the views that I put out in this presentation do not represent those of Lawrence Livermore, Sandia, or the U.S. government. Perfect. All right. So this project seeks to do a couple of different things. Substantively, it looks at the question of how military capabilities impact conflict escalation dynamics. In the news currently, there's a lot of hand-wringing surrounding new both nuclear and conventional capabilities and how they might be stabilizing or destabilizing with regards to deterrence, proliferation, and what have you. The problem traditionally with trying to adjudicate these policy debates is that we don't have data with which to actually interrogate them. And so the second part of our project is actually trying to create and design a new method for actually adjudicating these types of questions with this experimental wargaming approach. Obviously with regards to nuclear questions, our N is very, very small. We're talking about an N of 2, an N of 1, an N of 9, right, depending on what you're talking about. And so that's a big problem when you're trying to actually come up with, appropriate policymaking processes. It's also worth pointing out that traditionally, we've thought about nuclear deterrence relationships as being kind of stemming from a massive retaliation strategy. And there's been, a lot of literature that kind of explores ways to kind of get outside of that massive retaliation straitjacket. And so there's a number of scholars who spend time working on limited nuclear war, limited in a variety of different ways, right? Limited in terms of its scope, its duration, what the objectives are, what types of targets are appropriate. And then scholars also looking at the development and deployment of limited nuclear capabilities, both quantitatively, as in low numbers, and also qualitatively. And so we're kind of taking on that qualitative question here in this study and adjudicating what is both a historical and contemporary academic and policy debate. So you have scholars that suggest that the addition of limited nuclear capabilities might be stabilizing. Most recently, Bridge Colby and Matt Kronig suggesting that adding tailored nuclear capabilities to nuclear arsenals strengthens deterrence, increases the amount of military utility that you're able to get out of this particular capability, and demonstrates resolve to both adversaries and also to your allies. That allies component being really important when we're talking about extended deterrence relationships. On the opposite side, however, there's also scholars that suggest that these limited nuclear capabilities could be destabilizing, whether they're degrading the nuclear taboo, increasing the likelihood of accidental nuclear use, particularly as we close the gap between conventional and nuclear escalation ladders, and the danger that these capabilities might encourage spiraling behavior as an adversary fails to perceive that a nuclear capability is deployed in a limited fashion, and then you get an escalatory spiral from there. It's also important to point out that this is not just a debate that's happening on the academic side. It's very much a real policy debate. We see just in the last few weeks here, the Department of State Bureau of Arms Control and Verification paper that speaks to this particular problem set. But you also have policymakers across the globe looking at how do we decide how to build an appropriate nuclear capability set for the strategic challenges that they're facing. And so we're left with this research question that's kind of the brass tacks of the project. So how do tailored nuclear capabilities alter the threshold for nuclear use? And as I mentioned before, the major question is, okay, well, how do we actually test this research question? How would we go about answering it? Traditionally, we would go out, look at the world, and try to bring in as much empirical data as we can, whether that's case study analysis or ideally large N analysis. As I mentioned before, those don't exist in a nuclear case set, and that's a good thing. So in response to that dearth of empirical data, we're faced with a variety of kind of imperfect solutions, whether that's employing formal models in which you're making assumptions about how the world works, and often keeping your model very, very simple. Computer-based models, similar data generating process there with regards to making simplifying assumptions about the world. And then finally, using survey experiments that coming at this from a social science side are increasingly in vogue as ways to kind of look at these behavioral questions around international security challenges. Each of these approaches, you have various strengths and weaknesses. One of the kind of glaring problems with all of them is that they fail to create an immersive environment that even closely approximates the crisis decision making that individuals are going to have to go through as they're making decisions about what types of capabilities to deploy and subsequently use. And so our wargaming platform Signal, that's specifically designed to incorporate experimental design principles, seeks to try to address some of those problems. And so today I'm going to show you some results that come out of Signal Online. There's a picture of this here on your screen, where it's effectively an online terminal-based digital war game in which data collection is automated and we're able to collect some interesting things with regards to chat data. I'll also be showing you some results from the signal survey experiment that we use to validate the gameplay that we're getting in Signal Online. I should also mention that as well as these two products, the Project of Nuclear Gaming also produced a Signal tabletop exercise that we built out and carried out in Livermore in May of 2018. And we also have a Signal board game that served as the vehicle for iteration and building into the Signal Online. I'm more than happy to talk about the various design features of the wargaming platforms during the Q&A. So today I really kind of wanted to spend some time with the results. So for the Signal Online platform, there's two different types of data that we can pull out of this for analysis very easily. The first is at the game level, and the second is at the player level. As we're making decisions about kind of what data we use from the platform itself, we created several exclusion criteria that we think are relatively defensible. The first is that a game for our purposes has to last at least 3 complete rounds. The game itself can go on for 5 rounds in the Signal Online. It can go on for as many rounds as players would like in the board game version. We also only use those games in which no players are dropped. So the Signal Online is a 3-player online game. For those of you that have ever played online games in the past, you'll know that players dropping out because their Wi-Fi is poor is a problem. It's also a problem with Zoom calls. And so we didn't want to include games in which it shifted from being a 3-player game to a 2-player game with a player dropping out, right? Because obviously the dynamics in a 2-player game are probably going to be different than in a 3-player game. And for the first blush analysis, we don't want to compare apples with oranges. And we also only use those games in which the demographic survey information is completed by all of the players of the game. So for the purposes of the analysis, we have 426 games in the analysis that I'm going to show you. There's actually over 1,000 games inside of the large repository, but using the inclusion criteria, this is what we have to work with. And there's also 853 nuclear players of 1,362 total in the game. The reason that I'm only using nuclear players is that we're interested in creating a control treatment design where we're really testing this nuclear capability question, right? And so you don't, again, want to include non-nuclear player behavior in that analysis. Here are some of the kind of the first set of results that I want to show you. Just by way of background, what we're doing here is we're comparing a control game in which players are not given tailored nuclear capabilities to a treatment game in which they are given additional tailored nuclear capabilities. In this case, they're being given high precision, low yield nuclear warheads and electromagnetic pulse nuclear warheads. Inside the game itself, it makes it very clear to the players that these are nuclear capabilities. And so I'm using a logit model here to predict the probability of nuclear use, represented by a z-score here across 4 different models. And so what you're getting shown here is that as we move the treatment from control at 0 to treatment at 1, what the impact of the z-score or log odds of nuclear use is. And you can see that here we're finding support for the null hypothesis, which is that these additional tailored nuclear capabilities are not having an effect on player behavior inside of the wargaming environment. Here I'm also showing you a series of demographic variable controls. And again, there's nothing that's very, there's nothing here statistically significant about how these different demographic characteristics are influencing player behavior. However, this will shift in just a second here. It's also worth mentioning that along with the logit model used for prediction, I've also run an OLS and a probit model and also a heteroscedastic logit just to kind of check that the modeling parameters aren't the thing that are driving the findings, and we find this null this null effect to be consistent across all of these model types. Moving down to the player unit of analysis, we start to see a little bit of interesting data coming out of the model, different interesting analysis coming out of the model on the covariates. We also get to ask a slightly different question as we kind of shift down here our unit of analysis. So we can ask both, were nuclear weapons used inside of the game by the player? And we can also look at who the players are that are using nuclear weapons first. So here you have models 1 and 2 showing nuclear first use, models 3 and 4 showing the probability of nuclear use in general. Again, with regards to the treatment that we're interested in, this nuclear capability set, there's no difference as we add in these tailored nuclear capabilities. What we do find, however, is that our female players are significantly less likely to use nuclear weapons first. They're also less likely to use nuclear weapons overall, but the finding is not statistically significant in that case. The other one that gets fairly close to statistical significance is reported knowledge. So the more our players self-report knowledge about international security and nuclear deterrence issues, we see that their probability of nuclear use drops. The p-values in this case are 0.11 and 0.13. So it's starting to get close. So just kind of wanted to highlight that here as well. To validate the method, we use a separate methodology. And so here, what I've built out is a survey experiment. That's a 3-stage 3x3 factorial design that gives our respondents to the survey an advisory role. So unlike inside of a war game where you have to live with the decisions that you're making inside of the environment, here we're asking the respondents to the survey to suggest to a national security advisor, what would you do here? And again, we're varying the same capability set as in the experimental wargaming platform. So we're comparing across those respondents that are given tailored nuclear capabilities, high yield nuclear capabilities, and what have you. The scenario that they're given are designed to as closely approximate some of the situations that you might find inside of the signal war game as possible. Of course, there's no way to get a 1-for-1, but the 3 stages allow us to look at how military basing in a near neighbor might affect respondent answers, how a cyber attack might affect respondent answers, and how an adversary putting their nuclear forces on high alert might impact respondent answers. And so you'll notice that none of these are particularly aggressive, and that's by design, right? Like you don't want to try to be pushing your respondents to have a very kind of aggressive response to a scenario. You want to kind of allow them to bring themselves into it and make these types of decisions. So like in the Signal Wargaming platform and in the survey, we try to keep things as kind of non-aggressive as possible. And when we actually cut into the survey data and we compare respondents that have have no tailored nuclear capabilities to those that do have tailored nuclear capabilities, we're again seeing no difference here. And that's looking at both advising nuclear use and advising nuclear threat. And so that suggests that at least for across these 2 different data generating processes, we're kind of seeing the same kinds of results. Of course, this project has a variety of different applications that are kind of being worked in progress right now. Currently, I'm working on geotagging some of the data. So one of the nice things about having the kind of map-based platform in a war game is that we can look at where players are actually acting on the map, either economically or militarily. We also have chat data for text analysis. We also are looking at using existing conventional conflict escalation data and comparing that against the wargaming data, either by taking out the nuclear components and just kind of looking at the patterns of escalation over time. We're also looking at the laboratory effects, looking at how elites, those with significant foreign policy expertise, might play differently than non-elites. We're also looking at various ways to extend the wargaming platform to incorporate human-machine experiments. And we kind of have two major efforts looking at new designs altogether. One is a left of signal game that looks not at how players use capabilities when they're given them, but actually looking at when players decide to actually proliferate nuclear capabilities. And so that's something that's in the works. And then we have a project with NATO that looks at how players might cooperate with each other inside of a competitive environment to face specific challenges. So it's kind of neat to see these various extensions come out of this first kind of methodological dig at what is a very difficult problem. Before I wrap up, I also want to take a moment to thank Professor Veach and Dr. Goldblum for their support during my time as a PhD candidate and postdoctoral fellow at Berkeley. I've engaged widely across the labs, visited Los Alamos, spent a year at Lawrence Livermore as a pre-doctoral fellow, been to Sandia, both in Albuquerque and here in Livermore, and the Kansas City nuclear security complex as well. This engagement has actually led me to my next role. So I start on Monday at Sandia National Labs in 8710, the Systems Analysis Group. And so, without this experience, that wouldn't have been possible. I've also leveraged a number of the trainings that NSSC had provided, starting with PPNT, that was the beginning of my journey, and have had the opportunity to engage with a variety of other professional development opportunities via CSIS's Pony program as both a scholar and mid-career cadre. And the other thing I'd like to highlight is that I serve under Bethany as the Deputy Director of the Nuclear Policy Working Group, which is a student-led organization at UC Berkeley that seeks to provide a space for undergraduate and graduate students, both from technical and non-technical backgrounds, to learn about nuclear issues in a non-advocacy and non-partisan environment. And that was a lot of fun. And it kind of culminated for me in introducing the panel that was discussed earlier with Governor Brown and Secretary Moniz, as well as Bethany and Corey Henderson from NTI. So with that, I'll end and look forward to your questions.
Thank you, Andrew. So we have a number of questions, so we'll just get to it. So how does a change in an adversary's policy, such as a guaranteed nuclear counterstrike in response to a conventional strike, apply to your work and perhaps complicate it?
Yeah, it certainly complicates it. So as we're building out these wargaming environments, we have to decide what types of capabilities we want to give an adversary. And it's up to the players to actually communicate what their capabilities are and when they're willing to use them. And so what we've done here in this initial run is actually only compare symmetrical capabilities. So in a lot of ways, what this abstract wargaming environment is picking up is two near-peer competitors that have identical nuclear capabilities across one another. In the survey experiment, because the cost of N is far, far lower, we actually test the asymmetrical cases. And there we actually have some really interesting findings of where these capabilities actually are changing things. So for example, when we had the asymmetrical cases and we have players given these additional nuclear capabilities that are not given to the adversary, they're much more likely to be used. But it does require, on the design side, right, it's a slightly different way of designing it to have that asymmetrical use case. And so for this first run, because it's a proof of concept for the method, we wanted to make sure that it was kind of as clean as possible. And so we wanted all of our N to come from that symmetrical case.
Thanks. And maybe a bit of a similar question. What key parameters do you change when you compare war games for, say, a high-tech modern conventional war versus a nuclear war? And how would you or do you fight them in the same way in the virtual environment?
Yeah, so again, this is only instrumented one way. So this is only instrumented with nuclear capabilities included. And so we spent a lot of time with folks from Lawrence Livermore actually trying to make sure that our weapon effects, whilst abstract, were, you know, more or less in line with kind of our understanding of them with regards to the physics. It is almost certainly the case that if you take away the nuclear capabilities and just play this game conventional and conventional, that the escalation patterns might change. And so that's work that's TBD. Again, because the cost of N is lower, we actually managed to do that work in the survey experiment. But again, in the first run, we're only really comparing nuclear to nuclear. But I think there's good reasons theoretically to think that the escalation ladders are likely to be different in the conventional versus conventional case. I should also mention as well that, you know, because we don't want to increase the cognitive load on players beyond what is absolutely necessary, it does require abstracting some of the capabilities out, right? So we use cyber attacks inside of Signal as a way of doing a disabling attack, right? Which is obviously not the only way that you could use cyber capabilities, right? So if you wanted to design a game that was really pushing out that conventional question, I probably suggest that we want to make sure that the capability set is maybe built out more in that conventional basket, if you will, that again, more closely approximates the capabilities that are available. So, you know, we're only providing, you know, 8 or 9 capabilities to our players in order that they can actually kind of spin up on it and play in a reasonable period of time. And so we're abstracting a lot, right? And so if you're going to optimize for just conventional, you're going to want to spend more time kind of building that complexity out. But it's certainly one of the things, you know, that we're going to do, because that's the easiest way for us to actually compare against existing empirical data and actually to validate the method.
Thanks, Andrew. We're running out of time, but I think you can answer this last one quickly. So would the outcome on female players change with ethnicity, racial attributes, etc.?
Yeah, so there you want to run a slightly different model with interaction effects to get at each single one of those. Currently, there's no reasons to think that they would, given that no other covariates seem to be doing a lot of work beyond the self-reported knowledge, right? So the extent to which that's a kind of an ethnic characteristic is, you know, debatable, but it's a common control. And so you want to interact them. And so we can certainly do that. It's just a matter of there's nothing on its face from the models to suggest that ethnicity or player origin is having work here. I should mention that one of the interesting challenges for this project is that it's spitting out game as the level of analysis in that kind of first basket of results. And the problem there is that traditionally we're only looking at like how one person's demographic characteristics impacts behavior, but here we have to aggregate it across all 3 players inside the game, right? And so there's a lot of work that we had to do there methodologically to actually make sure that we're comparing the same things. And so, you know, again, you'd end up with 9 different possible cross matches if you're going to use 2 different covariates inside that 3-player game, if you will. So it's been a really interesting methodological hurdle for us to jump over.
Thanks. And Andrew's contact information is also available on the event page if you have additional questions that we didn't have time to get to today. Thanks so much for all the interaction here, and thanks, Andrew, for an excellent talk. Professor Yasmina Buic, would you like to say a few words before we close?
Just few closing remarks. So first, I would like to thank our NSSC fellows that presented excellent, fantastic talks. And these were actually comments on our question and answer list. Also, I would like to point out that today presentations were related to one focus area, which is nuclear and particle physics, and 2 cross-cutting areas. One is nuclear security policy, and the other is nuclear data. Tomorrow, we will review two focus areas. One is radiochemistry and forensics, and the second one is radiation detection and measurements, and one cross-cutting area, which is modeling and simulation. With that, we start at the same time, and my talk tomorrow will give highlights of all focus and cross-cutting areas. In addition to that, I would like to thank to our sponsors. Some of them were also present today. Thank you, Randy. Bell, also to our colleagues from national laboratories and other federal agencies, as well as our colleagues from universities and our students. So with this, I would like to close today's session. So please join us tomorrow.
Thank you. Have a great afternoon. Bye.